Hey everyone, my name is Vikram, this is Chenggang. We're both grad students at UC Berkeley. First, I just want to say thanks to everyone for being here, and thanks to the craft organizers for putting on an awesome conference. We're super excited to be here. So, serverless computing is something a bunch of folks at Berkeley have gotten really excited about recently. And one of the reasons why is because, as we all know, everyone is learning to program nowadays. Up here, these are a bunch of fifth graders in San Diego who are learning to program by playing Minecraft, which is not really something I ever expected. But maybe more interestingly, this is our introductory CS class at UC Berkeley last fall. I was a Berkeley undergrad. When I took this course, it was, I don't know, like 300 or 500 students. This last fall, it was about 2,000 students. The class was so big, in fact, that they couldn't fit it in any of the lecture halls we have on campus, so they actually put it in the concert hall. And as you can maybe sort of see in this photo, the concert hall was actually almost all full except for that very top deck over there. In addition to these 2,000 students, every semester there are about another 1,000 students at Berkeley who are learning a new data science curriculum. And they're doing things like data processing and maybe some simple machine learning tasks in Python, usually using Jupyter notebooks and running on some sort of hosted infrastructure. Most of these people aren't computer scientists. They're biologists and economists and chemists and so on. And they're using some sort of simple programming to help make their lives easier, right? But importantly, they don't have a traditional software engineering or computer science background. They don't know anything about Kubernetes or Docker. And so a really interesting question that we've been thinking about is how we're going to make these folks productive, especially if they're not going to be working on powerful laptops like we're used to, if they're running on Chromebooks or running on some sort of hosted infrastructure. A really important question is where their code is going to run. And the answer is obviously in the cloud. I mean, if it wasn't in the cloud, I wouldn't be here talking about this. So what we're going to sort of do in this talk is first take stock of what exists today. Why is serverless cool? Why do we care about it? What can it do? And then we're going to talk about some of the sort of gaps, right? Where does existing serverless infrastructure fail to meet the needs for the kinds of applications we're interested in? And then we'll talk about some new work that we're doing to try to start filling those gaps and talk about where we're headed. So, serverless computing. In case anyone's been living under a rock and doesn't know what serverless is, I skipped a few slides. Okay, serverless computing. This is, I hope, a pretty unobjectionable definition. There's a lot of different definitions of serverless that are floating around. But roughly, we define serverless to be a programming abstraction where users can upload their code, run them at any scale, and pay only for the resources used. There's a lot of really popular offerings. Lambda, I'm sure you're all familiar with. All the other major cloud providers have some. There's some open source ones as well. But at a high level, all of these are optimized for simplicity. The point is that you go there, you register some functions, you enable triggers. So up here, these are some example triggers in the AWS ecosystem. You can have an API gateway, maybe some Alexa skills, or uploading a new key to S3, those sorts of things. And you scale transparently. If you run one request, you only pay for the time that one request ran. If you run 1 million requests, you pay 1 million times that. And if you run 0 requests, importantly, you pay $0. So the sort of canonical example of FAS is something like this. You upload a new profile picture to Twitter, and Twitter is going to generate a bunch of different thumbnails, one that goes on your profile, one that goes on people's timelines, one that goes in that little bar at the top where your account settings are, and so on. And you want to pre-generate all those thumbnails. And if you were running this on a cloud server, you would have to do things like worry about fault tolerance. How do you make sure that you have multiple replicas, you can deal with load? If one of the machines crashes, how do you make sure that you actually process all of those images so you have the right version of the thumbnails and so on? FAS, on the other hand, allows you to do all of this transparently. It deals with the fault tolerance, it deals with the deployment, and all you have to worry about as the application developer is writing the code that does the image resizing and putting it in the right place in the cloud storage and writing the path to the database and so on. And then you're done. So why serverless? Well, sort of already hinted at this. But the idea is that today's cloud abstractions are pretty hard to use. I don't want to make anyone angry. It's undeniable that application development tools have gotten a lot better. Kubernetes is sort of the best of server-based computing. It gives you things like automated fault tolerance if containers fail. It gives you things now like coarse-grained auto-scaling. And that's great, but at the end of the day, all of these things are oriented towards infrastructure folks. They're not oriented towards application developers. And if you're not a computer scientist like all the folks in those CS classes I was talking about a few seconds ago, you're definitely not going to be able to understand how do I stand up a Kubernetes cluster, how do I deal with the deployments in Kubernetes and so on. That's going to be pretty difficult. So serverless is really cool. It starts solving some of these problems. And oh no. Okay, I keep clicking too hard. So there's been a bunch of academic interest in serverless. There's been a bunch of papers on some cool work. We've written some of them at Berkeley. But of course, sometimes we get feedback like this on Hacker News. This is an actual comment that was on one of our papers that got posted to Hacker News. So I want to convince you that there's not just academic interest, but also industrial interest. We're in Silicon Valley. There's a lot of cool startups that are working on making serverless more usable and helping folks deploy serverless applications and so on. But maybe even more excitingly, these are just a subset of the companies that are using AWS Lambda today for a variety of applications. And this is just from the AWS use cases website and not taking into account Google or Azure or Microsoft. So what are all these folks doing? What can you actually do with functions as a service today? There's two key things that FAST is really good at. The first is embarrassingly parallel tasks. These are things like image and video processing, like I was talking about a second ago, ETLing data into storage systems, any sort of task that doesn't require coordination, where the requests are usually idempotent, and things that are purely functional. The output just depends on what data you're putting into it. The other thing that FAST is good at is workflow orchestration. So this is an example workflow from, I believe, the Autodesk use case on the AWS website. And it includes something like, here on my notes, 24 Lambdas, 12 API gateway calls, 8 database accesses, and 7 SNS notifications. And what Lambda is used for here is to basically coordinate all of these different tasks. So you need to access some databases, do some integrity checks, make sure that you send the right email out to the user. And according to this example on the AWS website, this took Autodesk's account sign-up workflow from taking 2 weeks to 10 minutes. I'm not sure how it took 2 weeks in the first place, but fast is good for some stuff. And that's great, but if you move past these kinds of embarrassingly parallel tasks or this workflow orchestration stuff, you start to run into some walls pretty quickly. I'll talk about what those are in a second, but in case any of you are from the major cloud providers, this is some feedback we get pretty often when we talk about serverless. We work with a lot of folks from Google and AWS. They're sponsors of our lab, and they sort of raise their hands and they say, hey, I've built this serverless service. It's called Google Cloud Dataflow or AWS Glue or Athena and so on. And all of these are really awesome services. They auto-scale, they take into account data locality and all these good things that we want. But at the end of the day, they all offer some pretty limited programming models. So Cloud Dataflow allows you to write Spark programs, Athena gives you SQL, and so on. And what we're really interested in, for our purposes, is generality. We want to support general-purpose programming in the serverless mold with all those nice guarantees I was talking about a few minutes ago. Okay, so getting back to FAST, what can't you do on FAST today? Well, these are some pretty common limitations that you hear folks talk about. Things like limited execution lifetimes, right? So on AWS Lambda, functions can only be 15 minutes. On the other cloud providers, it's something like 9 or 10 minutes. Inbound network connections are disabled, so you can't open up a port and listen for requests like you do when you're building a web server, for example. And I/O is a bottleneck. So as we all know, S3 gives you really great bandwidth. But to get that bandwidth with Lambda today, you actually have to spin up a massive number of clients, like tens of thousands of clients. And even if you get really good bandwidth, latency is still going to be a bottleneck if you're doing any sort of data-intensive task. And finally, you get no specialized hardware. So if you're doing something that's very compute-intensive, you want GPUs or FPGAs or something like that, you have no access to those things. In this talk, we're going to focus on the middle two. The first one has actually been consistently getting better over time, and we think it's really a configuration thing. So when AWS Lambda came out, it was a 1-minute lifetime. It became 5, and last year at reInvent, they upped it to 15. And the specialized hardware thing, we think the cloud providers are probably going to address in short order. But so we have these middle two limitations. No inbound network connections, and I/O is a bottleneck. But that's actually okay, right? Because everything is just functional programming. We can all write Haskell-like programs. It's called AWS Lambda, after all. So, it must be functional. And functional programs don't have side effects, and they don't have mutable state, so it's not a problem. Except that's not actually true. And as much as Haskell Curry and Simon Peyton-Jones may want that to be true, Simon Peyton-Jones is the inventor of the Haskell language, this is not actually how real applications are built in practice. And we'll dive into that more in a second. But what that means is that if you're trying to write software on fast infrastructure today, you're not getting functions as a service, but you're actually getting something that's more like dysfunction as a service. And that's because real applications share a state. They share state in a variety of ways. One, it looks like function composition. So I have some function g of x that executes. The results are the argument to some other function f. Well, today, that has to go through a really slow, faraway storage system like S3, or you have to do some hacks to get it to pass state transparently. So that's kind of tough. Network connections, this is a natural way in which applications share state. They pass messages to each other. If you work in distributed systems, you may implement something like Paxos. If you're doing some sort of distributed aggregation, that's a common use case. But all of these things require some low latency message passing. And if you don't have that, then you're going to have a bad time. And then the third one is modifying shared mutable state. So you have a database, you have a bunch of different distributed compute, and they're all talking to that database, and you need a way to think about what are the consistency guarantees you get from that database, how do you get performance out of that. And these things may all sound pretty simple, but it turns out if you try to do them on fast infrastructure today, it's pretty difficult. And fast is, at the end of the day, really poorly suited for all of these things. So I'm going to hand it over to Chenggang now, and he'll tell you a little bit more about where fast is insufficient and sort of what we're working on to try to make it a little bit better.
OK, thanks, Vikram. So now let's dig a little bit deeper and talk about the pain points of running applications on fast today. And as we go, it turns out that we're going to disappoint some of our famous computer scientists. So imagine, you have a simple sequence of tasks, something like, looking up user information, looking up their Netflix browsing history, and make some predictions about what they'll want to watch next, right? So that's a really simple sequence of pure functional operators, and we want to know how it performs on Lambda. But in order to isolate its performance overhead, we just pretend that these functions are entirely instantaneous by just letting them doing some simple arithmetic operations, and just deploy a simple sequence of two functions. But as we deploy these two functions on Lambda, we found that there's no natural way for these two functions to pass argument. So as our first cut solution, what we end up doing is after this first function finished execution, we write the result into storage systems like Amazon S3 and Amazon DynamoDB. And the second function basically reads in these results, performs some simple computations, and returns to the user. But as you can imagine, the performance of both of these options are very slow, actually up to 200 millisecond latency. So the reason behind this high latency is because we're going through the storage systems, right? So the next hack we tried is to hard code this function chaining into the program itself. So what I mean by that is at the end of the first function, we just manually add a Lambda function invocation call to the second function. But this is actually not how users are supposed to be using Lambda, because when the second Lambda function executes, the first one is still hanging there and waiting for the result, right? So Amazon is still going to charge us for that. So it's not so ideal. But nevertheless, it reduces the overhead of going through storage. So as expected, the latency of that yellow bar is much lower, but still kind of pretty expensive, around 100 milliseconds. So finally, what we tried is to use AWS Step Function, which is an orchestration service specifically designed for running this DAGs of computations. So hopefully this will reduce the overhead compared to the previous two implementations. But as you can see, it turns out to be even slower, the blue bar. And by the way, if you execute the same workload locally on your laptop, it turns out to be actually 4 orders of magnitude faster than using all of these services. It's quite astonishing. So to summarize, even if you're just writing pure functional programs, you're still going to pay very significant performance overhead. So these two guys are still not going to be happy at all. Okay? And to make things a little bit more complicated, right? As we mentioned a few slides ago, real-world applications are not purely functional. So they do have state, and in most cases, they have shared mutable state. So for example, say you're building a web application that spans across many different servers, and these servers may have shared access to a database, right? So in this case, the stuff that you store inside that database is shared mutable state. So as mentioned earlier, right, because the current fast offerings are entirely stateless, so what these applications are doing is to store these state in a separate storage engine. And as you can imagine, different cloud providers have like 10 different storage options offerings, and each of them have different trade-offs across the ability to auto-scale and consistency models provided and the performance characteristics. So we said, okay, we expect that we'll be able to find at least one such service that fits the serverless ideal of being both auto-scaling and low latency. But as we play around with these services, we found that there just seems to be a tension between this auto-scaling and low latency. So for example, auto-scaling storage options like S3 and Dynamo actually imposes a latency penalty of up to tens of milliseconds, even for really small reason writes. And on the other hand, low latency storage systems like hosted versions of Redis and Memcached, actually they are surprisingly not very auto-scaling because it requires manual provisioning to scale the systems up and down. Of course, one can just always provision for the peak load, but that's very anti-serverless because it wastes a lot of money here, right? So for our purpose, we basically ignored any system that's not auto-scaling because in any realistic applications, it will soon become a pretty big bottleneck. And in addition, today's auto-scaling storage systems tend to offer pretty poor consistency guarantees. So for example, at a first glance, maintaining something like a shared counter seems like a pretty trivial task. But for those of us who worked in distributed systems, we know that sometimes this can get notoriously hard to get it right. So say if I store this shared counter in S3, and multiple people just trying to simultaneously read the counter, do some local increment operations, and write it back to the storage, then sometimes the update will be overwritten by the others, introducing inconsistency. So, Jim Gray, the father of modern databases and also a Turing Award winner, will be pretty upset about this consistency model. And, by the way, we do want to acknowledge that there are services today that's starting to offer stronger consistencies, like Amazon DynamoDB recently announces this transaction mode, which offers you stronger guarantees, but, at a cost of latency and dollar penalty here. So to summarize, there really doesn't exist a single cloud storage system today that simultaneously offer auto-scaling, low latency, and rich consistency models. So finally, as we said before, current fast offerings, they doesn't allow functions to communicate directly with each other, right? So, we were actually just complaining about, not having inbound network connections, but I do want to acknowledge some of its benefits, including, disabling inbound connections enables cloud providers to easily do process migration for a load balancing purpose, for example, and it also facilitates fault tolerance. But the problem is if we want to build real distributed applications on top of fast, then different functions, sometimes they do need to talk to each other, right? And since direct communication is blocked, they're forced to, again, communicate via the storage system. So what happens is that one function can write a message to a well-known location in the database, and the other function can simply periodically pull that location to retrieve the message. Right? But as I mentioned before, this is just extremely, extremely slow. And real-world high-performance distributed applications, they just cannot tolerate such high latency. So with the current fast offering plus this slow storage, we're basically throwing away the entire distributed computing textbook. And Leslie Lamport, another successful computer scientist, also Turing Award winner, will be very disappointed about this fact. So, but today, we're not here to just complain about fast, right? But as Mr. Chekhov might tell you, we have an idea of how to fix that. So by now, hopefully, we've convinced you that there's still a long way to go to run stateful serverless applications. And this is actually relevant to both non-CS programmers as well as expert developers, because recall that it even requires some hack to even get the simplest two-function chaining to work on Lambda. And if you're a serious developer, working on real distributed systems, then you'll have to worry about trade-offs such as auto-scaling, consistency, and performance stuff. So, in the spirit of being constructive rather than just criticizing stuff, we've been actually trying to tackle some of these challenges and make serverless computing more general purpose. And so the direction we've been headed in is to make a state management easier in the context of serverless. So, as the name suggests, instead of just pure functional programming, we also want to embrace state. But embracing state is a challenging task because, as I mentioned earlier, a successful state management system or storage system needs to simultaneously address the issue of auto-scaling, low latency, and consistency models. But for us, fortunately, Vikram and I have worked exactly on that during our PhDs. So in the last couple of years, we built this high-performance distributed storage engine called Anna, which offers really, really fast performance, actually 10 times as fast as Redis. And also, it quickly adapts to workload variation in a cost-efficient manner. But due to time constraint, I don't have time to go into technical details. But if you're interested, feel free to look at these papers I listed below or come talk to us after the talk. Okay? But the overall message here is that we already have a storage system that can act as a backend of a fast layer for developers to build stateful serverless applications. So we've been building a system called Fluent, which is a fast layer built on top of Anna. So I know the system's name collides with the name FluentD project, so we're trying to come up with a better name here, but for now we'll just stick with Fluent. So the design goal is to first keep all the goodies of the current fast offerings, so especially the disaggregation of compute and state, so that the compute tier and the storage tier can scale independently of each other. So these fast systems like the Lambda, pioneered this disaggregated architecture, and we do want to acknowledge some of its benefits. So from the user's perspective, it reduces costs and makes auto-scaling of both tiers extremely simple. That's very good. And also from the cloud vendor's perspective, it enables this very fine-grained bin packing of the compute and storage resources, which leads to very high utilization, which is the holy grail of cloud computing. So in addition to maintaining this disaggregation, our next goal is to solve all of the limitations that we listed before in order to make serverless a viable option for stateful applications. And the key to achieve all of this is to use Anna both for storage and a communication medium. But simply replacing a slow storage like S3 with Anna is actually not sufficient. Because although Anna is already orders of magnitude faster than S3, in order for the fast layer to talk to the storage layer, we still need to go across this network boundary, right? And if we have some distributed applications that really require ultra-low latency, then sometimes this network latency is not tolerable. So one key insight to solve this issue is that logical disaggregation of compute and storage should not preclude physical colocation. So what I mean by that is that logically, you can still think of this compute tier and storage tier to be two completely different services, scaling independently. But when we actually implement these two layers, we can do some tricks, play some techniques to collocate data close to the compute node. Actually, ideally collocate them within a single machine to completely eliminate this network latency. So as you can imagine, the simplest technique is via caching. Very simple. So 40 years of computer science already taught us that caching definitely makes things faster, And then communication and function composition can be achieved via a fast pass on top of the Anna key value stores puts and get. And in case there are some machine failures and network partitioning, we can still use Anna as a communication medium, despite with the cost of paying this network round trip overhead. But the problem is just adding caching is actually not sufficient to solve all of our problems, because we now have shared mutable state both at the storage tier and also at the compute tier. So a new challenge is that maintaining the consistency across these states. Right? So as we've already seen, sidestepping this consistency issue is definitely not a good idea. Right? So it turns out that this is a pretty challenging technical problem, and we spent quite a bunch of time researching this issue, but we ended up using some of our ANA's consistency mechanism to be able to provide a wide range of different consistency models by encapsulating the program state into a lattice data structure. So this is captured by one of our recent paper submission. So if you're interested in the technical details about how we achieve cache consistency via lattices, please feel free to come talk to us afterwards. OK, so with Fluent, right, let's revisit the performance of our previous function composition microbenchmark. So as we can see, Fluent's native support for function chaining led it to actually outperform Lambda by over 2 orders of magnitude. And similarly, for all the other limitations we listed, including things like data locality, auto-scaling, consistency issues, and direct communication stuff, we have relevant benchmarks to show that our system actually beats state-of-the-art by orders of magnitude. But rather than just going through these performance graphs one by one, let me instead show you a real-world case study in machine learning prediction serving that we built on top of Fluent and how it performs against the latest solutions. So the goal of prediction serving, short primer, is to generate predictions from pre-trained machine learning models. So these tasks are typically actually pretty computationally intensive with low latency requirement. And actually, also in practice, generating one prediction requires going through a sequence of operations instead of just one. So as shown in this figure, typically we go through the phase of we first clean the input data, and then we join it with some reference data. And then instead of just executing one model, we typically want to execute multiple replicas of that model to improve its statistical accuracy. And finally, we gather this result and normalize the output. Okay? So as you can see, this is exactly function chaining and should be a perfect fit to FAST. Right? But as you can imagine, we run into the same issues as the previous function composition benchmark. And in addition, these prediction serving tasks in general requires pretty heavy data movement between different nodes. So it generates actually pretty expensive overhead on current fast infrastructure. So how do people actually do this in production today, right? Well, it turns out that folks at the major cloud providers are developing specific systems for tackling these issues. So one example is AWS SageMaker, which provides an end-to-end machine learning model lifecycle management framework. So one of the tools they offer is for the developers to actually deploy the model prediction pipeline just as the one I just showed you. So what we did is we want to compare Fluent against this state-of-the-art solution. So we basically went ahead and implement the pipeline that I just described with the SqueezeNet model, which is a state-of-the-art image classification model developed actually at Berkeley. So SqueezeNet actually aims to create a smaller neural net with a fewer number of parameters with the goal for it to actually easier to fit into computer memory. And it's generally oriented towards running on edge devices. So think about stuff like autonomous vehicle. Okay? So we deployed this pipeline both on Fluent and SageMaker and compared against their performance. And guess what? We can easily outperform SageMaker by up to 3 times without even trying any specific optimizations. And one of the main reasons that we can outperform SageMaker is that SageMaker actually does not allow parallelism across these different operations, while Fluent does. So in our example, right, when we execute these multiple replicas of models, Fluent can detect that, OK, there's no dependency across these tasks, so it can just execute them in parallel across multiple compute nodes. Whereas for SageMaker, it actually executes these model prediction tasks one by one in a serial fashion. Okay? So that explains the performance gap. OK, so let me now hand over to Vikram to talk about our vision for the future of cloud programming.
Cool. So The whole point, the whole reason that we've been thinking about this, like I was saying at the beginning of the talk, is trying to think about what cloud programming is going to look like in the next 5 or 10 or 15 years. Looking back, we see that SaaS has innovated in terms of the guarantees that it makes. It makes it really easy for the average developer or non-computer scientist to get started, run some code, and have it scale transparently. But there's some key limitations. Functional programming is really slow. Function composition doesn't work well. Communication is forced through slow storage, which means that you can't do any of the distributed message passing in whatever context that you might be doing it in. And you get really poor consistency guarantees. This last one is particularly insidious because you might not think this sounds very hard, but when you start reading and writing from storage systems and ending up with random gibberish or not even being able to read the value that you just wrote, which actually can happen on some of these storage systems, it makes it really hard for you to reason about what in the hell your application is actually doing. So what we've been doing is trying to make fast functional, not in the functional programming sense of the word, but just making it work. So we've been doing things like embracing state, which allows us to make some easy things a lot better, right? Like our function composition allows us to go significantly faster than before. Harder things like this machine learning prediction serving task become easier. And obviously, we're not claiming to support the full production-ready features that a system like SageMaker supports, but just by building a simple prototype and being really nitpicky and thoughtful about the overheads that we're introducing, we're able to provide performance that's significantly better than what exists today. And we think, in general, this is a step on the road towards a more programmable cloud. The vision that we sort of have is that serverless will change the way that we think about writing software. And really excitingly, as sort of folks who do research on infrastructure, it's also going to change the way that we think about building that infrastructure. In particular, thinking about how we program the cloud is a really interesting challenge. There's never really been a way to think about programming, millions of cores and I don't know, petabytes of data, right? But that's actually the sort of scale of resources that's available in the cloud. Most applications don't need that, but for those applications that do, there's no way to really think about that. And getting from here to there is not super obvious. Getting from the programming models we have today to the models that'll allow us to do these crazy kinds of things is not obvious. So moving forward from fast, looking into what we think are the sort of key challenges that will actually make serverless more general purpose and more usable. Obviously, we've talked about state management already, and that's a really important one. And we think that's sort of one of the key enabling first steps, but there's a bunch of other things too. The first one is building developer tools. I mean, we all already know that building distributed systems is tough, and debugging them is even more difficult. And now if you throw FAS into the picture, you can no longer SSH into the machine and read logs and do all the crazy things we do to debug distributed systems today. And so providing observability and enabling people to understand what's happening across these function chains, especially as they become longer and more complicated, and making it easier for all of these people who are not computer scientists and aren't distributed systems people to be thinking about how their applications fit together. What are the tracing tools that they have? What are the testing tools that they have? That's going to be a really important enabling direction. Another one is auto-scaling policy. We sort of think that having a general purpose autoscaling policy is maybe not the best idea. And in fact, it's not even super clear that for a wide variety of applications, you're going to be able to build one. Today, if you make more requests, you get more cores, right? But that doesn't necessarily capture all of the full variety of ways in which one might choose to autoscale. There's been a bunch of cool work at Berkeley, actually, from our lab on doing some more proactive autoscaling of resources in response to load spikes and trying to predict those load spikes. And this is particularly important when you have production applications that have performance deadlines and so on. And if in the Lambda use case, in the Lambda infrastructure, if you run into a resource limit, you basically wait for another EC2 VM to come up, which can take 30 seconds or a few minutes or something, which doesn't really fit into consistent performance, which ties into my last point, which is designing SLOs and SLAs for this stuff to work well is going to be really important. This one's more oriented towards the software engineering folks who want to use Lambda rather than the non-computer scientists. But I think a key blocker for adoption of Lambda is getting consistent performance out of this infrastructure. And having SLOs and SLAs for these applications is going to be really tough because, as you can imagine, if my code takes 50 milliseconds to run and yours takes 50 minutes to run, it's not clear what your SLO versus my SLO should be. So thinking hard about what these contracts are, what are these agreements between the cloud provider and between the user, and how we can start designing these performance guarantees is, I think, really interesting, but also really, really important for making this stuff useful. So that's all we have for today. We've been working on this open source project called Fluent, like Chenggang mentioned. We just had a paper deadline a couple weeks ago, so the code is really messy. So look if you're interested, but look at your own peril. We also have the paper that we submitted. It's a double-blind conference, so we can't share it publicly. But if you're interested in what we're working on, we're definitely happy to chat more. And please do reach out, tweet it as email if you're interested. We'd love to hear what you think if you're writing serverless applications and so on. And so thank you for listening.
Look at that, almost perfect timing. Can we get the Slido up, please? Okay, gents, we're going to follow the usual way of doing this. I'm going to read the questions. I'm really good at reading. You're going to answer them. I'll let you fight over which one of you answers. And I'll stand here so it doesn't get physical, okay? Question number 1 from our good old favorite Anonymous. Aren't you really comparing apples with peaches with SageMaker?
So that's a good point. Like I said, we're definitely not trying to say that we're a production-ready system and SageMaker is much worse than us or anything like that. The point here is really that for these really performance-sensitive tasks, of which machine learning prediction serving is one, because oftentimes it's run in interactive web applications, which have a few hundred millisecond deadlines, introducing these very high overheads is maybe not always tenable for those kinds of applications. So it's totally fair to say that it's not an exact comparison, but we're really interested in showing that our infrastructure, with, again, being very, very thoughtful about the kinds of overheads we're introducing, is able to outperform a purpose-built system for that particular task.
Cool. Next one. Couldn't you use something like pub/sub or pub/sub or Kinesis to compose lambdas?
Yes, it will be slow, right? AWS Lambda today, from what we understand, uses SQS, which is a pub/sub style system under the hood, and that introduces latencies on the order of 30 to 50 milliseconds per request. It provides very strong message delivery guarantees, something like, I think SQS allows you to get exactly once message delivery, but it doesn't allow you to get low latency. So there is a sort of fundamental trade-off there.
Next one. Any tips to design application now, what can be moved later to serverless easily when all these problems are solved?
Interesting. Do you have any thoughts, Chenggang?
I don't really understand the question.
So I think, in general, the sort of trend towards more granular programs, things like microservices, and even the sort of logical endpoint of that direction is really moving to functions, right? Beyond that, I think this idea of having separate state management or separate systems that do state management from the systems that are responsible for compute is going to continue to be an integral part of this. Like we were talking about, the logical disaggregation of compute and storage is really important, and it's going to be. I don't think that's going away, right? So if you're not able to separate out your state from your compute and deal with compute instances appearing and disappearing over time, then I don't think it's going to be super easy to port applications to serverless.
Okay, we'll do one more, gents, and it is, why do you think that real-world apps need low latencies? There are many real-world apps launched with Lambda, S3, and Dynamod already.
Yeah, so it's definitely true that many real-world apps, some of them they don't need low latency, right? They're already deployed pretty successfully in this existing cloud infrastructures. But we also want to emphasize that there are another groups of applications. For example, is machine learning prediction serving, right? That do require low latency, and some of them not only requires low latency, but also require some SLO guarantees. So we still have a long way to go in order to achieve all of these.
Yeah, we're definitely not trying to claim that we're solving all the applications in the world, or even that all the applications in the world are going to use serverless. I mean, today there are still folks who hack on the C kernel and write assembly code, but we also consider that to be a much lower level kind of programming. than writing even in C++ or Java or something like that. In the same way, there will always be folks who are allocating VMs and containers and managing the scaling of their applications manually. But for the general purpose use case, we think there's a lot of potential in being able to do this stuff really fast and with low overheads.
Awesome. Round of applause for the gentleman again, please.